couple of just quick review here and get this together. Okay, so let's just talk definitions wise. We start with the basic form of matter, which is an atom, right? We know that atoms have three parts to it, or particles. Your protons and your neutrons, which are in the nucleus. Protons are positive, neutrons are neutral, and your electrons are negative, and they kind of float outside the orbit in a constant movement. They're attracted by something called binding energy. Those electrons and those protons are connected by this binding energy, that opposite negatives attract deal. Okay, so within that kind of attraction is a lot of energy inside that. And when we go to harness that or move it or influence the break of that binding energy, we can harness that energy into something called that electromagnetic radiation, and that's how we get X-rays. So again, atoms make up molecules. A bunch of molecules together make up matter, so that's us, right? We know that matter has many different forms. We know it's solid, liquid, or gas. We know that energy is the ability to do work, which we want. We have a lot of those. We talked about what a photon is. A photon is a tiny bundle of energy. So that kind of cascades. That's going to be like our launch point here. We also talked about the Bromström radiation, which is that process of breaking radiation where we have a photon, which is that tiny bundle of energy, and it gets harnessed and it gets attracted to this proton, neutron, and the electrons going all around in this nice little atom over here. This photon or energy or electron, all of it is correct. Okay, all of that is right over here. Comes over and it goes speed of light, super, super fast, lots of energy, lots of momentum. And once it gets near that proton, it breaks. It slows down and it's able to kind of collide into one of those electrons that are flying around it, and it kicks off an electron, and that binding energy that's released, the photon over here will kind of decelerate and scatter to one side because we can't create or destroy it, right? We cannot create or destroy energy. It just gets harnessed, so it decelerates and becomes scattered to go away, or it gets absorbed in matter somewhere else. And then that binding energy that we kind of we stole that electron from, becomes electromagnetic radiation. Again, Bromström radiation, all those very complicated things when we're really just playing bumper cars with some energy, taking one form of energy, making it another, okay? Again, we're not creating or destroying it, we're harnessing it, we're changing it, we're utilizing it. You can say all of that, or if there's any energy that's left over, it's kind of getting absorbed by whatever matter's in the way, okay? A good principle. So does that, again, now that you've heard it like several times, that concept sound pretty good to you of how we get that electromagnetic radiation? Wonderful. We know that electromagnetic radiation, we know that process of gaining or losing an electron is called ionization. So it's either going to gain that electron or lose the electron. In our instance, we're losing an electron because that's getting harnessed somewhere else. So we're creating ionization. We're creating an ion, an unbalanced atom. Unbalanced is that key term here, that we're able to steal that energy and utilize it for something else. The three properties of X-rays, of electromagnetic radiation, is that electromagnetic radiation passes or travels in a straight line, meaning A to B. It doesn't make a hard right or hard left, just straight line. Travels at the speed of light and travels in a wave-like motion. Short wavelengths, long wavelengths, okay? Go crazy here. Somebody's trying to get onto system. Okay. hold on one second. Let me just send a link to somebody that's getting stuck here. So 3 properties. Now, the laundry list of items for characteristics are a lot, right? So there are some properties that are involved in characteristics. And again, properties are what makes electromagnetic radiation unique. Characteristics are what describes them, okay? It's like brown hair is a characteristic and breathing air is a property, okay? It's one, it defines it, one is describing it, okay? Okay, so the characteristics, it's invisible. It cannot be detected by your senses. So we cannot touch it, taste it, see it, hear it. It has no mass or weight. It has no charge, believe it or not. They, again, travel at a speed of light, travel in wavelengths, short wavelengths, and high frequency. That's the best part of it. It also travels in long wavelengths, but again, we don't want long wavelengths. They don't really penetrate, right? They're the ancillary of it. We want to eventually get rid of those. They travel in a straight line, but once it connects with matter or hits matter initially, it deflects and scatters. Electromagnetic radiation is absorbed by matter, by our skin, by our tissues, just like sunlight, okay, just like visible light. It causes ionization, again, gain or loss of an electron. It can cause certain substances to fluoresce, meaning that energy, like a neon sign, if it hits it with enough energy, it will fluoresce, it will light up. It can produce an image on photographic film. Again, we use digital type of image receptors now, or digital programming. But if we didn't and we had regular film, that would be the photographic film that we're talking about. It kind of stains it on like a Polaroid or old school film, if you could imagine. And it causes changes to living cells. So again, that's what makes radiation an issue, is because of us. If we get excessive exposure, right, then we absorb it, and that's going to cause tissue damage for us, whether it's long-term or short-term, like something like sunburn. Now, that's review. Now tonight we have our new stuff. So this will start the new part of this series here. So the X-ray machine itself, regardless if it's an extraoral or an outside machine that's going to take an X-ray from outside, an extraoral like a panoramic or a cephalomeric or even a CBCT scan, those are extraoral. Intraoral, which we take X-rays inside the mouth, no matter what, the machine has 3 major parts regardless. You'll always have a tube head. That's where the action happens. You're always going to have an extension arm. That's where all of our cords and our wires and our electrical equipment is. And you always have a control panel that is going to allow us to choose settings, okay, and turn the machine on and off. So those are going to be the 3 main parts, no matter what, okay? So now we're going to pick each of those parts out and kind of describe them and give information about them. So we're going to start with the more complicated one, of course, the tube head. All right, so this has the most information or the most parts inside the tube head itself. So we're going to start from outside in on the tube head. Now, the tube head itself is typically housed, so the outside can either be a plastic or aluminum or even a metal body. So it's okay what the outer part is. It's going to be the inside that keeps us safe, okay? So let's look at it from outside in. So if the outside is either a metal body or an aluminum body, it will have the next layer will be called the tube head seal. And that is a lead liner that surrounds the entire inside of the tube head. Makes sense, right? That it's going to be a lead line because any energy that's derived in there, we don't want to escape out. Like you hit a button and radiation's everywhere. That we don't want. We want to harness it and we want to direct it. So that entire tube head itself is going to be lined with a lead or what's called the tube head seal, which is made of lead. The next layer in is going to be what's called insulating oil. That insulating oil is necessary. Remember I said that deceleration, that photon that kind of breaks and scatters out? And we're going to name that as called heat. Okay, it's going to be a lot of heat that generates in this energy bind here when this electromagnetic radiation is occurring, when it's harnessed and all of that. So if I were to say 100% of electromagnetic radiation, that's a lot. So what is actually happening there is 99% of the energy that's harnessed actually will get absorbed into that oil as heat, okay? And only 1% of that electromagnetic radiation is useful, okay? That is what we're harnessing. So 1% radiation is what we're getting, and 99% is going to be absorbed in that insulating oil. And it's truly oil. It's just a bunch of oil inside that tube head that's sealed in with that with that lead inside that tube head to absorb 99% heat there. Within that, the next thing, there is something called the X-ray glass tube. Ah, that's where all the magic happens. That is what we were talking about the other day with Wilhelm Röntgen, who invented that. It's a 6-inch glass tube, about 6 inches long and about an inch wide. We're going to get a little bit more into what that glass tube is shortly. But I just want to describe that. That is where the heart and soul of the whole X-ray machine is, no matter what type of machine it is. That is where we're going to harness our energy and kind of fundamentally make that electromagnetic radiation. Now, transformers. There's going to be 2 transformers that are going to be inside the tube head. Now, what is a transformer? A transformer is the areas where it alters the amount of voltage or energy that's coming in from electricity from the wall socket. Okay, so does everybody know what a transformer looks like out in the world? Those big green boxes that we see on the street. And did you ever hear, oh, it got hit by like lightning or something crazy and a transformer blew and the power went out, right? So what transformers are, I would, to put it in layman's terms, they're the mediator that takes all the energy that's getting supplied. And in order for it to come into our houses, it has to kind of control the amount. One, so it doesn't blow up all of our electricity, right? All of our electrical appliances. So typically what a transformer does, it's going to step down the amount that's getting brought in. So it's literally a transformer. It's going from one type or one amount to another. Okay, so let's say it comes in at 110 volts. It's going to step it down to 10 so that our homes and in this instance, our X-ray machine has the right amount of volts, not too much to burn out all of our equipment. Does that make sense? So if a lot of electricity is coming in or at a high voltage, it's going to step it down. Typically it's 110 volts out in the world. We're stepping it down in our X-ray unit to about 5 or 10. That's a lot. That's a big step down, right? That's very little power that we need to harness this energy to get electromagnetic radiation too. So just imagine that 110 volts coming in, boom, stepping right down almost to nothing, to 5 to 10 volts. So really impressive there. Now, on the flip side, if not enough voltage is available, then that transformer will step it up. It will increase the amount of volts that are needed. Let's say we're in a brownout and there's not an electricity like in the summertime when it's a lot of heat and it's really hot outside. Our AC is cranking. You may have not a lot of energy to expose here. So transformers will step it up. It will increase the energy that we need, those volts to be used. So that's all a transformer does, is step it down or step it up depending on how many volts is needed for us. The next part of a tube head is the lead collimator, okay? That lead collimator is going to be part of what the tube head seal is, right? So we know the seal is made up of lead. So the collimator acts like a lens. It acts like an opening. So the tube head seal creates that lead collimator. Does that make sense? It's like where the lead kind of comes into here. So we have a lead lined box, but we're going to focus and end it at what's called the lead collimator or the lens or the hole or, the opening to where the electromagnetic radiation is going to go through. Okay. So the lead collimator is basically a lead disc in the positioning indicating device, which is like that lens piece, that long lens piece. And at the end of here, I'll put up a picture of a tube head in a few minutes. The collimator is actually by the manufacturer will limit the size and shape of the beam. The ADA recommends the lead collimator, that shape, to be a rectangle because it's about the same kind of diameter or size of either film or a sensor. So it reduces the amount of radiation exposure around that. But we also see circular as well. Either is fine. They just recommend the rectangle to eliminate the amount of exposure, of the tissue exposure, but it can be either a rectangle or circle cylindrical. Now, the next kind of piece that we need to kind of put in play is the aluminum filter, right? We need to filter out those long wavelengths that we don't need in our electromagnetic radiation. They are useless. Long wavelengths do not penetrate matter. They just bounce off of them and just expose us to radiation that's unnecessarily. What we do want are those short, greater wavelengths that have high penetrating power. That's what we want. They go right through that aluminum filter with no problem. So the aluminum filter acts as a filtration. It's going to remove the non-penetrating long wavelengths, and it's about 0.5 millimeters thick. That's how thick the aluminum is, okay? Not crazy amount, but just enough to get out those long wavelengths. So that is one of our safety precautions as well, is that aluminum filter. The PID stands for position indicating device. Okay, just in case, I know those vocabulary words we had last week, but PID stands for positioning indicating device. All that means, if you ever saw a high-powered lens on a camera, that piece that sticks out, the zoom lens, that's what a PID looks like. It's the long piece that kind of focuses in on the beam itself, which we want. The longer that positioning indicating device is, the better, or the more the better quality picture we get. Okay, so it's favored to have a longer PID here. It's just the open-ended, it is lead-lined cylinder that extends from the opening of that metal housing out. Okay. I want to get, okay. Now, these are the main parts of the tube head. The housing, which could be either a metal body or aluminum, doesn't matter. The insulating oil, your tube head seal, which is essentially lead sealed or lead lined, right? We have the X-ray glass tube where all the magic happens. We have a couple of transformers that are going to step up or step down the amount of voltage that comes in. Our lead collimator is going to be that lead disc that is going to shape or limit the size beam that we're using for exposure. We want it rectangle by ADA is recommended, but we have cylinder and rectangle. The aluminum filter is the next part. It is going to filter out the long wavelengths and just give us the short wavelengths here, so it could be the most penetrating and the safest. The thickness is 0.5 millimeters. And the PID, which is the positioning indicating device, is basically our open-ended lead line cylinder that is going to direct the beam. Okay, we put that PID wherever in direction of where we want to hit. Okay, that's like our focal point, our focus there. Awesome. Any questions with this part of the tube head, the intraoral or extraoral machine? Again, all of these parts are in the same type of X-ray machine. Now, we have to do a little bit of a deeper dive into the X-ray glass tube, because this is, again, is where all the energy is getting harnessed and where it transitions from plain electrons, electricity, to electromagnetic radiation. So again, the glass tube is about 6 inches long, 1 inch in diameter. Remember what I said last week is all of the air or oxygen has been vacuumed, removed from that glass tube. It is completely airtight sealed. There is no air in there. Why? To remind us, if there's air in there, that means there's molecules that will run into our electrons. And if they ran into that, they will become sluggish and not give us all the power that we need. Does that make sense? So when there's no restrictions, that energy, those electrons are going to have no restriction or nothing else to hit into to create little mini things that we don't need. It's literally going to give us that energy from going from A to Z. Okay, just that's it, and all the power to it, which is a good thing. So it's vacuum sealed inside there. Now, we want to get rid of the resistance is why we have that. Now, there's two main parts in that glass tube. One part of it is called the cathode, and that is the negative type of electrode. Okay, that's the negative portion of the glass tube. What that negative portion, that cathode, consists of, we're going to have a really popular metal here called tungsten. Okay, we talked a little bit about tungsten last week. Tungsten is very sensitive, or it attracts electrons. It loves them. It can't get enough of them. Electrons is like, oh my God, tungsten. It's like us and diamonds. It's like girls and diamonds. We can't get enough of them. We have to drape ourselves around with them. So tungsten and electrons have that same affinity to each other. They love them, okay? So tungsten filament, if I say filament, I mean nothing more than a very light string of this tungsten, very thin, very dainty kind of metal that's going to sit in that cathode, okay? So if you ever looked at an old school light bulb, you see like this filament inside of it, right? Even the new light bulbs, you see this like electrical thing that lights up. That's tungsten. It gets excited by electricity and electrons. So it's no matter what, we're using the same technology here, okay? So in the cathode, which is the negative portion of it, there's a tungsten filament, which has a attraction to electrons, and something called a focusing cup, okay? The purpose of a focusing cup is to actually hold back those electrons until we're ready to use them, okay? So you have a cathode, which is going to have that tungsten filament. Now, the cathode is just the negative portion. The whole side that's negative is called the cathode, okay? It's not like one piece. It's the the thought of the tungsten filament, the focusing cup, that whole area is called the cathode, which is the negative part of that electrode, okay? Like the whole gamut of it is cathode. Now, the focusing cup again is going to hold back or secure or suspend those electrons in that cloud where that tungsten filament is until we're ready to press our exposure button. Once that happens, our focusing cup comes down, those electrons is going to go to the other side of the electrode, which is going to be the positive electrode, and that's the anode, A-N-O-D-E. That's the positive portion of the glass tube. Embedded in a piece of copper, okay, so you'll have a piece of copper. Embedded in that copper, you have another piece of tungsten. It's like a block of tungsten embedded in a block of copper, okay? We call that the tungsten target. So it's in the positive side. There, why we have copper there, I talked about 99% of this is going as heat, right? What's a great conductor of heat, everybody? Copper, okay? That's why copper pans are wonderful. So copper is going to absorb that 99% heat that's getting generated upon those electrons, boom, ramming into that target, that breaking radiation. That's what's happening right there. So the heat gets absorbed in that copper stem, we call it. And 1% is going to push through that target and get out to what we need it to be, okay? That radiation beam that we're looking for. So to look at this, the copper conducts the heat away from the target. It also helps reduce wear or reduction of wear. So we're not like, going through these parts so much. The target is going to act as a focal spot, meaning a concentration of where the energy is going. And here it's converting those electrons, that energy, into our X-ray photons or electromagnetic radiation right at that area. Now, the insulating oil at this point is absorbing all of that 99% heat from that copper stem directly into the insulating oil. So that's where that energy is going. It gets absorbed and it's gone. That 1% remains is going to exit our tube head through the opening of the PID, and then it's going to hit whatever image receptor we have. Isn't that crazy? That is sophisticated to get electromagnetic radiation. And I want to reduce this to like, oh my God, right? This is as complicated as this may seem. We're just taking energy from our wall that's coming in from the world, right? And harnessing it and making it this very penetrating power to be able to see through bone and tissue. I mean, it's like boom. And it takes nothing but like a fifth, 10th, 9th of a second to create that. That's amazing to me. In that very small amount of time, with very little equipment, very tiny little equipment, we're creating enough power to see through things we can't see through. It's crazy. It's amazing. It's a miracle, so they say, right? It's science. It's cool. Any questions on this? So really, glass tube portion, there's just two parts to it, really. The negative part, which is the cathode, and your positive part, which is the anode. And knowing what little pieces go with that. Tungsten filament, where our electrons are going to hang out, and our focusing cup. And then our copper stem that has the tungsten target embedded in it in the anode positive portion of it. So those are the very little pieces here that operate in this. Any questions? Jess, does that make sense? Yeah, cool. Mandy, Gerline, Kristen, Mariah, Dejay, any questions here? Does that premise of where we go from one type of energy to convert to another? No? Good?
Yes. Mm-hmm.
Oh, awesome. Good, good, good. Okay. Love it. And again, you can text me or email me any questions, of course. So now let's kind of dive a little deeper into a couple of other parts of this, like a little deeper dive in that. We started with the X-ray tube, glass tube. Now we're going to talk about the PID, the position indicating device. We know that it's lead lined, needed to be lead lined. Why not? If it was aluminum or plastic, that primary beam would do what? It'd come out and go like it would just scatter immediately. It would be crazy, right? We're like, oh my God, it's, we can't see it. So we wouldn't, if we can't say it's blinding us, but we would know that all the energy is getting exposed everywhere. So we know it's lead lined. We're using it for the aim. It's going to aim the beam at the film or sensor or the tooth area that we're trying to take the picture of. We know it's open-ended and we want it placed as close to the face as possible to get a clear shot. So the closer it is to the film, we know we're not going to have any divergence or scatter. It's going to be very focused. The focal point is going to be very close to the, we're not going to get any magnification. Let's put it that way. It's going to be very clear, high definition. We know that it comes in two shapes, cylindrical and rectangular. Now, again, we're going to suggest that the rectangular one is going to be recommended because it limits the size of the beam. Only because our image receptor, our film, our sensors are rectangle, that they're rectangular. So they figure if our beam is rectangular, it'll be less exposure outside. Does that make sense? It's just minimizing the exposure. And of course, we want to minimize exposure on patients. It is not mandatory though. That is PID, that's the positioning indicating device. Now, the extension arms, the easiest thing that you can, you're like, oh, this is the easy part. This is the easy one, only really one thing. It's just where the wires are coming from the control panel to the tube head. So it is where the electricity is traveling from the control panel, the wall, to the tube head to give that energy through. That's the extension arm, no matter what machine we're looking at. It's the easiest thing to define there. Now, control panel, pretty easy too. What's on a control panel? So the control panel has the master switch, turn it on and off. It has to have an indicator light because you need to know, oh, is it on? Because if it did not have a light indicating that it's on and somebody by accident hits an exposure button, what's going on, right? You're going to be exposing people left and right all over the place. So it has to have master switch, indicator light, your selector buttons, and your exposure button. We'll come back to selector buttons in well, it's going to be right here. Your exposure button basically is is what we use when we're getting ready to expose an X-ray. It's going to force that focusing cup down. So that's attached to it. So boom, focusing cup comes down. I grab my picture. Now, the selector buttons, there's going to be 3 types of selections that we have options to, or selectors on the control panel itself. The first one is the seconds, right? Time is going to show up on our control panel. How long are we exposing the X-ray for? The second one is called milliamperage or MA. The MA selector is going to be the measure, so quantity of electrical current that's passing through. So it's actually the number of electrons. So we're going to get into the range and show that. But as we know, milliamperage, amps are the energy. We heard about amps, right? If you hook an amp up to a guitar and lower it, you get low volume or low energy. You raise it up on an amp and you go, rah, heavy metal head busters here, headbangers. So MA is milliamperage, amps, and it's the measure or quantity of electrons or electricity or electrical current. I'm saying the same thing. I'm just using different words, guys. Okay. That's passing through and that we harness in that area of that. So it is a range. We typically range the MAs between 7 and 15. Okay, 7 is ideal, 15 is super high, but it can range on the control panel dependent on the frame of the human that we're taking an X-ray on, okay, or the machine itself. Okay, now the kilovoltage or kV is kilovoltage. We also call it kVp, which is kilovoltage peak. That is the amount of volts that come in. We know volts means quality. It means that penetrating power, right, guys? It's how much of that penetrating power is coming in. How much are we harnessing that? So kVp, kilovoltage peak, has typically a range between 70 or 90. Now, we normally cannot change that setting. That is a manufacturer setting. So it's either going to, but I'm going to say this, newer models will give you a range of 65 or 70 that you can actually hit back and forth on, newer digital models. Older models, it was either 70 or 90. You cannot change kVp. So we're going to go under the assumption that we cannot change kVp. That is going to be preset in a control panel. Okay, let's just say that out loud to us. So kilovoltage peak or kVp is penetrating power in volts, and it is already a preset selection on the machine. Very rarely can we change that. That everything that I just said is going to mean something very shortly, okay? Because you're like, well, if I can't change the kVp, well, what settings can I change, right? That should be your next kind of like logistical question. Then what do you mean? If I have a child coming in and I can't change that, what do I do, right? If I have this penetrating power, but I have a little child, oh my God, I don't want all that energy in there, right? So what do? There are settings that we change. kVp is not one of them. kVp is the master of the power, okay? It is the penetrating power. It is the master. It controls the quality, the diagnostic of the X-ray, okay? It's what makes it pretty. It's what makes us see the things inside the X-ray, okay? And the range will operate again between 70 and 90, and it's preset and typically can't move. Awesome. So those are the parts of the X-ray machine itself. Check, 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 and check. Tube head, extension arm, control panel. We now know that we've taken apart the tube head. Fantastic. We identified all the parts in the tube head. We focused on the glass tube where all the magic happens. Great. We talked about each part of that tube head in its entirety to the descriptor of what it does, how we utilize that. We also talked about the settings a little bit and kind of started going, we know what penetrating power, we know what controls that, we know what controls the quantity of the electrons, and we by definition can understand all of that information. How do you guys feel so far with that? How we're breaking this down, like start to finish. Now we're going to end the last little bit on how we're actually creating X-ray production. Ignore review on page 594. I typed it. Did I type it? Everything that we're talking about here is really self-explanatory. Like we already kind of talked it through. So think of X-ray production as you want to start with electricity is coming in, right? It's coming in from outside. Awesome. Turn on the machine. Master switch is on. Indicator lights on. All those electrons or electricity is going to go through. We're going to choose our settings, whatever those are. We'll talk more about, we're going to dive deep on the settings on Thursday. all of those electrons are going to go through my extension arm, through the wires, through my transformer, and into my cathode. Does that make sense? Turn machine on, electricity or electrons come in. It's going to go through my extension arm, through my transformers to either, it's most likely going to step down the amount because it's going to come in hot here, okay? Step down, and all my electrons are going to hang out in the negative cathode in my X-ray glass tube. That focusing cup hangs them, it's just like backing those electrons in, it's holding them back. I'm ready for you, coach. Put me in, okay? That's what's happening there. The moment that we're ready to expose, hit the exposure button, my focusing cup drops down. All of my electrons, because I have no resistance, right? It's a glass tube with no air in it, hit my anode, my tungsten target that's built into my copper stem. That's the breaking radiation right there. That interaction is harnessing or converting into my electromagnetic radiation, right? 99% is heat. It's getting absorbed in my copper stem out to my insulating oil. My 1% that remains is electromagnetic radiation. That is my primary beam. It's called primary beam. It's called primary radiation, central ray, central beam. All of that is the same thing for the 1% energy radiation, electromagnetic radiation coming out, going through, getting shaped in my lead collimator. Right now, I'm going to either make a cylinder or a rectangle. It's going to go through my aluminum filter to get out all those long wavelengths, just my short wavelength. And then it finally goes out my PID. That's X-ray production. That's it. You're just walking through the parts. Okay, so we'll do it one more time. Electricity coming in from the wall. Electricity going through my extension arm. Electricity getting stepped down or stepped up in my transformer. My electrons hanging out in my cathode, my negative section. I hit exposure button. My focusing cup drops. My electrons hit my anode, my tungsten target. 99% heat is getting absorbed in my copper stem. 1% radiation is going to go out through the lead collimator to be shaped into the size and shape that we need, either rectangle or cylindrical. Then through the aluminum filter to filter out long wavelength, and then out PID. 10 steps. If you just go in the order of like how it looks, okay? Does that kind of make sense how it's kind of traveling through? Not terrible, right? Not terrible, good. Now, a couple of things to remember here. We know that voltage coming in is like 110 to 220. We only need 3 to 5 volts, so we're most likely going to step down at any rate here, okay? Now, I'm going to stop sharing my screen. Give me a second. I'm going to go online and show you a picture of a tube head in the glass tube so I can point out a couple of things, okay? Just give me a moment. She is, okay. Let's see. Here we go. Boom. This isn't bad. Not bad. This is, it's just a little drawing here. You guys can see this part of it? Okay. So this is, and I'll jump through a couple other pieces here. So dental X-ray tube. Here's where the cathode, the negative, the focusing cup, it literally looks like a little area, like a little backdrop of it. We know that the other side, I hate this picture. Let me see what picture I like here. This one's pretty. There we go. Can you see this one, guys? This one's a lot nicer. So our focusing cup here is this piece. This is the tungsten filament. It's just a lot of, like, it looks like a little thin filament, little curly Q here. My little electrons are gathering around here in the cathode. So this whole section is the cathode. This is the copper stem, this blue part here, and it's positive. It's indicating positive. This gray piece is our tungsten target. It's showing the electrons hitting the tungsten target. 99% of it is kind of scattering or absorbing into the copper. It's showing like absorbing into the world where our insulating oil will be on the outside of this tube. And then that 1% is going to get harnessed out through the area here. Well, here it's going to target it down and then out your PID here, okay? Let me see, I'd like to look at a couple of things. All right, let me pull up one last thing here. Give me a second. Okay. Perfect. There you go. Not bad. Okay. Boom. Okay, so this is a pretty decent picture here. This is showing the tube head, our step up and step down transformer, our glass tube that we've looked at a bunch, our metal housing here all the way on the outside, our insulating oil inside. We see our aluminum discs here that are that are actually going to filter out the long wavelengths, and our tube head seal, which is that lead collimator shaping that size, this circle of area right here. Let's see. Those, and the PID is like that whole piece that's coming down from that. Does that, when you see it inside, does that make sense? How it's like kind of stepping through and walking ourselves through it. Again, this is why I wait 2 days in between to move on anything else and review, so it sinks in and you're like, now I get it. If you are anywhere near x-rays, for if anyone's around, go to the rooms in the back, look in the PID, and you'll see a metal circle dead center. That's the aluminum filter, and the circle around it is the lead collimator. Okay, so you can actually like see it through there, see it through the PID. These are the pieces. Does anybody have any questions? Or let's see, there's a few other pictures, but they're all pretty much saying, again, the same thing of where everything's located. That's what this it happens to be. This looks like a complete metal tube head here, which is fine. This one actually is like a plastic with a lead lining inside. It looks like, I can tell by like the shine here. This is the PID portion of it, okay? If we're looking at it that way. I wanted to see, this is the PID. So whole tube head, this is tube head, and then this is the long PID. This is the extension arm that's starting to come down here. That's not what I wanted at all. Awesome. Okay. All right. Guys, that's everything. I'm getting discounts here. Cool. How does that feel? Not crazy, right? Not bad. You guys are great. So for Thursday, I would start looking at some vocabulary like radiolucent, radiopaque. Really look at the definitions defining kilovoltage peak, milliamperage, because we're going to dive in deeper with how that contrasts, density. Knowing those definitions for Thursday a little bit ahead of time will be, I think, a little helpful for you. Okay. All right, my friends. It was great.
I have a quick question, Ms.
Thank you.
Lawrence.
Yeah, shoot. Yes,
What did
please.
you say you were going to send the recordings? Because I wasn't able to
Oh,
come by there last week for class. I
I
just want to
am
make
so,
sure of that.
Kristen, I'm going to send them right now. You read my mind, and I'm so sorry. I
No,
will
that's
send,
okay.
I'll send them all. I'll just send them. My
Awesome.
bad.
Thank you so much. I appreciate it very much.
No problem. That is my fault altogether. I don't know what happened to me on Thursday.
That's okay. Things happen. It's all right. All
Thank you.
right. Thank you. Have a good
You're
one.
welcome. You too. Does
Bye.
everybody else need access to them, or are you guys good?
I do.
I'm
Yes.
good.
You do too. Okay, thank you.
Sorry.
All right, I'll send. You know what? I'll just send the link, like an email, and just boop 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 all three of them. Okay.
Okay,
Cool.
thank
Thank
you.
you.
Yeah, that'll be
You're
great.
welcome, guys. Yeah.
I
guys.
sorry, I won't be at the Thursday class. My son has a concert.
Oh no, we'll have fun. Yeah, I'll send you the recording.
Okay, thanks.
All right, sweetie. All right, I'll see everybody on Thursday. Bye.